Alright, this video is going to be more of a conceptual overview, just so you know what this topic or word means when you hear it, and we're not really going to do any math. So the question is, what happens if we take a sine wave, so I have voltage versus time. I'm going to just draw 2 periods there as an example, and we feed that as the input voltage into a circuit with a diode like this, a resistor R like that, and we're measuring V out here. So remember, this is different from what we did in the last couple videos where we had that flipped. We had the resistor first and then the diode with input and output, and we wound up with a voltage clipper. So we're not doing that. We have the diode first. The question, and you can assume that the amplitude for our purposes here of Vn is kind of much greater than the forward voltage drop across the diode. So we're just ignoring that tiny voltage drop across the diode. The question that I'm going to pose as a multiple choice question here is, what does the output voltage in this circuit look like? So give me a second to draw out all 4 of these options. So I have A, B, C, D. So does it just look like the input? Does it not change anything? Does it look like this? Does it just kind of keep the positive parts of the input while getting rid of the negative parts? Does it look like this? Does it do that but invert the input? Or does it make the input entirely positive? So think about that for a second. Pause the video, and then we will come back and answer this multiple choice question. Again, I am feeding a sine wave that goes positive and negative into this circuit, and then here I am plotting V out on the y-axis. What does V out look like? Okay, the correct answer to that question is B, and due to the shape of that graph, this circuit is called a half-wave rectifier. So our goal with rectification, that I probably should have mentioned at the beginning of the video, is to take AC, or alternating current, from a wall outlet and convert it to DC. So ultimately I want my output to be a constant, and this is very important for things like charging a battery. So all those little adapter thingies you have that plug into the wall to charge your cell phone, your laptop, many other devices where there's that little charger brick, as opposed to something like a lamp that just has an AC power cord and delivers the AC voltage directly to the load. That is what is inside these circuits, and you'll be able to find other videos online kind of showing a teardown of what is inside there, but we want to get from here to here, and diodes are not the full story, but they are part of that journey. So we call this one a half-wave rectifier because it is at least getting rid of the negative parts of the voltage. So we're keeping the positive parts, but then kind of clipping off or just making zero the parts that were previously negative. But we can do better than that. So we are going to go on to the next circuit that, instead of 1, uses 4 diodes. So this one is going to be a little more complicated to draw. This is the way you will usually see it drawn in a textbook. I'm going to have my diodes kind of in a diagonal configuration like this. I did a terrible job drawing that resistor. Let me try that again. Across a load R, where I have defined the positive end there and the negative end there. I'm going to have another diode like this. I'm going to have 4 diodes total here in this kind of diagonal or diamond configuration. There we go. And here is my AC voltage source Vs over here. So again, the question, I'm going to redraw your choices here. If my input voltage Vs is a sine wave that is going both positive and negative, what does my output voltage, which is now being measured across that resistor there, so across the positive and negative terminals I've defined on that resistor, what does my output voltage look like? And you can probably kind of guess based on what I hinted at, saying we can do better so far, but I'll do this as a multiple choice question anyway. A, B, C, D. Do I leave my input unchanged? Do I, oops, drew that wrong, invert it and clip off the positive part? Do I clip off just the negative part? Or do I make the whole thing positive? So pause it for a second and think about the potential answer there. So the correct answer here is D. And this circuit, instead of a half-wave rectifier, is called a full-wave rectifier. So not only did I get rid of the negative parts of the source signal, I actually flipped it and made everything positive. You may also see this referred to as a bridge rectifier. Bridge kind of being the word that is used to describe this circuit layout sometimes. So how does that work exactly? Let's do something I should have defined earlier. I'm going to define ground there, just so we have a reference for 0 volts. And remember that with an AC voltage source, that means that's my 0 here. So this side of the source can swing either positive or negative relative to ground, depending on which part of this cycle I'm in. So when I have a positive voltage here, that means current's going to flow this way. Gets here, go, okay, I can't go through that diode's backwards, so it can flow through this diode. Can't go through that one, that diode's facing the wrong way. It flows through the resistor, gets over here, and then it can flow through this diode, right? So we can kind of trace the zigzag path of that current, and note that it is going through my resistor from the positive to negative direction. So by convention, the way I've defined positive current and my sign convention on that resistor, the voltage I measure across that resistor is going to be positive. So maybe that's not that surprising, but the tricky part is when my voltage goes negative up here relative to ground, my current is going to flow in the other direction. I'm going to switch to my slightly brighter green. Let's see if I like that one any better. So my current is now going to flow this way. It gets here, can't flow through that diode, that one's backwards. It can flow through this diode, and can't flow through that diode, that one's backwards. It can flow through the resistor in the same direction and then go through this diode up here. So the configuration of the diodes keeps the direction of current through the resistor constant, even when the polarity of the source switches. So if I kind of draw, I have my positive parts there, just corresponding to the colors on the diagram, and the negative parts here. Even when the polarity of the source switches, because of how the diodes are laid out, the direction of current through the resistor does not change. Therefore, the polarity of the voltage drop across the resistor does not change. So I took the negative parts of that voltage and I converted them to a positive output voltage. Again, using the colors I used over here, I kept my initial positive parts of the source voltage. That didn't really change. But then I took what was previously those negative parts here and I flipped them positive. And again, I am ignoring that there is this tiny, say, 0.7 volt drop across these diodes. Assume the source is much bigger than that. For example, if you have 120 volts from a wall outlet, that tinier diode drop is kind of negligible. So again, that is why this is called a full wave rectifier. We have turned everything positive, but we still haven't really made it constant. Ideally, if we want to get a constant DC voltage to do something like charge a battery or power a device that relies on DC, this is positive, but we don't want to have these really big swings. And if you remember back from some earlier videos in this series, we looked at what happens if you drive an RC circuit with a square wave. So if we feed a square wave into that circuit, we saw the step response where the capacitor kind of takes time to charge up, and then when the voltage goes back down, it's going to take time to discharge, so on. So we ideally want to make this kind of constant as flat as possible. We can take the output of our rectifier and feed it into an RC circuit here. I'm going to use this in another color, so that when we charge up, we're charging up the capacitor, but then when this voltage goes back down, we have that time constant for the capacitor to discharge. So the circuit the output voltage is not going to discharge all the way before we then hit the next peak coming out of the rectifier, which charges up the capacitor again, and so on. So it's still not perfect, right? It's not a perfectly flat horizontal line. We have something called the ripple voltage. So there's going to be this tiny up and down movement of the voltage depending on the RC time constant of this part of the circuit, but it's much better than what we had originally. Remember, we started out with a sine wave that was fully positive or fully negative, and then we switched it to this all positive series of half waves. Then we feed it through that RC circuit, and we've gotten something that's pretty close to constant. So that is how we convert AC to DC, alternating current to direct current, and again have all of these wall adapters that do that and allow you to charge devices with batteries. So again, this was just really a conceptual overview. If you want to go into actually designing these circuits and picking values for the components and all of these things, that's going to be a kind of entire course on power supply design in its own right. But as a mechanical or civil or chemical or other type of non-electrical engineer, this way, when you see the phrase full wave rectifier or hear rectification, you at least know what the electrical engineers are talking about.